Today, we're going to dive into the hidden science that honestly keeps our modern world from just falling apart. We're talking about engineering dynamics, basically, how we figure out the motion of everything, from a tiny piston in an engine to the tallest skyscraper you can imagine. Let's get right into it. So, have you ever looked at a massive suspension bridge, swaying slightly in the wind, or a plane taking off, and just wondered, how do they know it won't just shake itself to pieces? How on earth can you account for all the crazy forces and motions at play? Well, that's the big question we're tackling today. How do we model a reality that is fundamentally complex and, a lot of the time, really unpredictable? So here's our roadmap. First, we're going to learn the basic language of how things move. Then we'll get to the fun part, where all those simple rules just completely break down. After that, we'll uncover the absolutely ingenious method engineers use to solve problems that seem impossible. And finally, we'll see how all this math actually shapes the world you live in every single day. All right, first things first. Before we can even think about predicting how a bridge is going to sway or how a wing might flex, we need a way to describe its movement in the first place. You can think of it like learning the alphabet of motion. Every complex system out there is built from these simple fundamental pieces. And the most fundamental concept of all is something called the degree of freedom, or just DOF for short. Now, put simply, it's just the number of independent ways something can move. So if you have a train on a track, it can only go forward and back, right? That's 1 degree of freedom. Easy. But what about an object floating in space? It can move up and down, left and right, forward and back, and it can rotate. That's way more freedom. And this, right here, is the essential starting point for any analysis. Let's look at a super simple example. This thing here is a slider crank mechanism. It's kind of like what you'd find in a car engine. This is a classic 1 degree of freedom system. See, if you know the angle of that spinning crank, you know the exact position of the piston. Their movements are perfectly, predictably linked. From a math standpoint, this is about as straightforward as it gets. Okay, but now, what about that satellite tumbling through space? It can move along 3 axes. We'll call them X, Y, and Z, and it can also rotate around each of them. You do the math, that's 6 degrees of freedom. And all of a sudden, predicting its motion is not simple at all. In fact, every new degree of freedom you add doesn't just add a little complexity, it adds an exponential layer of mathematical difficulty. This jump from 1 degree of freedom to n degrees of freedom, well, that's where the real challenge begins. And this is where we hit a massive wall. Because in the real world, things almost never follow those nice, simple, predictable rules. Most motion isn't a straight line. It's what engineers call nonlinear. And this is where things get really interesting. So, in some ideal, linear fantasy world, if you push something twice as hard, it moves exactly twice as far. The rules are simple, proportional. But in the messy, nonlinear, real world, a tiny push might do absolutely nothing. And then you push it just a little bit more. You hit a tipping point, and suddenly you get a massive, totally disproportionate reaction. This is the reality of large motions, of flexible materials, of all the complex forces at play. This quote from our source material here actually reveals a hidden rule. It says that for a system's motion to be simple and predictable, its energy has to behave in a very specific, orderly way, what mathematicians call a quadratic form. The best way to picture it is like a perfect, smooth, predictable curve. The moment the energy in a system deviates from that perfect curve, boom, you've entered the complex, messy, but much more realistic world of nonlinearity. And this is what that complexity looks like. Remember that simple 1 degree of freedom slider crank from a minute ago? Well, this is the real equation you need to actually describe its motion once you account for nonlinearity. Seriously, don't try to read it. Just look at it. Just appreciate that even for the simplest system, reality is incredibly complicated. Now just try to imagine what the math looks like for a system with 1,000 degrees of freedom. It's mind-boggling. So if the math is this monstrous, how do we build anything? How do we design safe bridges and reliable airplanes? It turns out engineers had to get really, really clever to find a way to work around this complexity. I mean, this is the billion-dollar question, right? If the actual math for a skyscraper or suspension bridge is basically unsolvable by hand, how can we ever be confident that it's safe? We can't just cross our fingers and hope for the best. We need a reliable method. And the answer is an absolute powerhouse of a technique called the finite element method, or FEM. The idea behind it is pure genius. You take a complex object, like, say, a car frame, that's impossible to analyze in one go, and then you break it down, you discretize it, into thousands, sometimes millions, of tiny, simple shapes called finite elements. Then you solve the simple math for each individual little piece. And finally, you stitch all those simple solutions back together to get a very, very good approximation of how the entire complex thing is going to behave.
So here's the key takeaway about FEM. It doesn't give you a single, perfect, exact answer. What it does is it trades an impossible-to-solve continuous problem for a massive but totally manageable discrete one. It basically turns the unsolvable into a problem that you can throw a bunch of computing power at.
Okay, so let's bring this all home. Degrees of freedom, nonlinearity, the finite element method. These aren't just abstract ideas in a textbook. These are the tools that literally build and safeguard the world we live in. And you see the applications everywhere. When an aerospace engineer designs a new plane, they use FEM to predict something called flutter, which is a super dangerous vibration in the wings. It's used to model how a suspension bridge will react to high winds, to simulate how a car will handle in a sharp turn, and to make sure the blades in a jet engine don't just tear themselves apart at 10,000 RPM. This isn't just theory. It is the absolute bedrock of modern safety and design. And let's look at a real concrete number, 44.741 Hertz. Now, that might seem random, but this is the calculated natural frequency of a simple beam. Why does this one number matter so much? Because if an outside force, say wind or an engine vibration, hits that beam at exactly this frequency, it will start to shake violently. This is called resonance. It's the same physics that lets you push a kid on a swing higher and higher with those perfectly timed shoves. And for an engineer, knowing this number is the difference between a stable structure and a catastrophic failure.
So, what we've really seen here is a journey, right? We started with this simple idea of just counting the ways something can move. We saw how that explodes into this mind-bending complexity in the real world. And then we discovered the powerful trick that engineers use to tame that complexity. This isn't just a bunch of math. It's literally the language we use to build our world safely and effectively. These powerful simulation tools have let us understand and predict the behavior of all the incredible things we've built. And it leaves us with this one final, fascinating question. As our methods and our computers get even more powerful, what complex natural systems, things like global weather patterns or even the folding of proteins in our own bodies, will we be able to model and truly understand next?